Everyone, it's Ranjit. Welcome back. In our previous discussion, we have thoroughly covered the drone's physical hardware, its software architecture, and the fundamental principles of aerodynamics and safety that governs its operation. Today, we're going into build on that knowledge and explore one of the most dynamic and rapid evolvement aspects in this field, the level of autonomy in drones. This is the point where the transition from the discussing a remote pilot aircraft to an intelligent, independent system that can perceive, decide, and act on its own. It is where all the components we have studied, the sensors, the powerful processing unit, and the sophisticated software, truly come together to create an intelligent behavior. Our agenda for this session is focused on the key technology that enables this autonomy. We'll begin by taking a deeper look at multi-rotor stabilization. We have touched upon the basics, but now we'll analyze the intricate feedback loop between the flight controller and the inertial measurement unit, understanding how it provides the foundational stability upon which all autonomous functions are built. From there, we'll explore the various flight modes available on drone modern drones. These drones are essentially different level of shared control between the pilot and the mission, ranging from fully manual to highly autonomous mode like position hold and waypoint navigation. We will also discuss the critical role of Wi-Fi connectivity. This technology is not just for basic remote control, it is a key enabler for advanced autonomy, facilitating the high-speed data transfer need for real-time video telemetry and even communication with cloud-based platform for advanced processing and fleet management. Finally, we will revisit the remote control operation, but we'll look at this through a new lens of autonomy. We will discuss how the pilot's role is shifting from the direct operator to a mission supervisor, working in partnership with the drone's intelligence system. And it will be my pleasure to guide you through this advanced topic. The concept we are going to cover today are the forefront of robotics, artificial intelligence, and aerospace engineering. Understanding the different level of autonomy is essential to understand the future trajectory of drone technology itself. This is what enables applications like self-flying deliver, delivery vehicle, intelligent agriculture monitoring, and automated infrastructure inspection. This is where the drone evolves from being just a tool to become an autonomous partner. So let's begin by examining some feature application where this autonomy is already making a profound impact. Truly understand the importance of autonomy, let's look at how it is being applied in real world right now across military, commercial, and public sector. Level of intelligence we are seeing is that system is already transforming complex operations. The military has been a driver of drone technology since a very long time, and autonomy is a key area of focus. The autonomous military drones are capable of operating both efficiently and inexpensively. The capacity of these systems are profound and raise raise significant ethical questions, as they are even being set to kill opposing soldiers. The prime example of this advancing technology is the Shield AI, the hive mind drone. This system is designed to assist both law enforcement and armed forces. It can operate in a complex environment, interacting with its surrounding to detect the environment and even recognize people, providing invaluable real-time intelligence and support, especially in an urgent situation. While military applications are powerful, the growth of autonomy in commercial and public sector is equally transformative. We have seen a rapid rise in automatic drone navigation, where drone use autopilot with built-in AI to follow checkpoints and perform automated patrols without direct human intervention. In the world of delivery and logistics, autonomy drones are being developed that are capable of carrying significant payload by up to 60 pounds and flying distance of up to 6 kilometers to deliver essential supplies and medical items. For surveillance tasks, AI-powered drone can now not only collect real-time data, but also analyze the data and make decisions independently. And in the precision agriculture, Internet of Things enabled, drone can autonomously follow preset flight path to collect data or spray pesticide with incredible accuracy. So, what does the future hold? The outlook is one of the continuous and rapid advancement. The process is artificial intelligence and deep learning with undoubted continues to enhance drone autonomy. We can expect to see drone with even more sophisticated decision making and problem solving capacity in the near future. This will lead to their increased integration into more sector, resulting in more efficient and safer operation across the border. However, this technology growth must be balanced with careful consideration of societal impact. As the system become more capable, the ethical consideration and the regulatory workframe that governs them will have to evolve right alongside of the technology. To understand how we achieve the stable flight needed for this autonomy, we need to revisit some of the core principles of physics. Before we delve deeper into multi-rotor stabilization and flight mode, it is essential to revisit two fundamental principles of physics that makes flight itself a possibility. Both fixed wing and multi-rotor relies on this core concept to generate the lift required to overcome gravity. These are Bernoulli's principle and Newton's third law of motion. Let's first look at Bernoulli's principle, which is illustrated in the aerofoil diagram. The principle describes the relationship between the existing speed of the fluid, like air, and its pressure. It states that as the speed of the fluid increases, its pressure decreases. This is critical for understanding how a fixed wing drone generates lift. The wing of an aircraft, known as an aerofoil, is shaped with a curved upper surface and a flattened lower surface. As these wings move through the air that flows around over the curved top surface must travel a longer distance than the air flowing underneath. To cover longer distance in the same amount of time, the air on the top moves faster, and according to Bernoulli's principle, the faster moving air exerts less pressure than the slower moving below the wing. This pressure difference between the top and the bottom surface result in the net upward force, which we call it as lift. While the Bernoulli's principle is key to understanding fixed wing flight, the operation of multirotor is more directly explained by the Newton's third law of motion. This famous law states that for every action, for every action, there is an equal and opposite reaction. This is the fundamental principle behind how multirotor drone achieves lift and thrust. The propellers are designed to act like fan, pushing a large mass of air directly downwards. This downward push of air is the action. In response, the air exerts an equal and opposite force back on the propellers, pushing the propellers upward. This upward force is the reaction, and this is the lift that allows the drone to take off and hover. It is important to note that this principle also applies to applies to the thrust generated by fixed wing propellers, which pushes the air backward to propel the aircraft forward. In essence, you can think of an fixed wing drone using a shape of the wing to create a pressure difference that pulls it into the air, while the multi-rotor drone uses its propeller to push itself up into the air. With these principles in mind, let's now look at how these are applied in specific design of fixed wing drones. For understanding of the core physics, let's now apply these concepts directly to the design and operation of fixed wing drones. Unlike multi-rotor that rely on pure vertical thrust, fixed wing drones are a masterclass in aerodynamic efficiency, using their shape to manipulate airflow and achieve flight. Key to fixed wing drone flight is the shape of its wing, which is called as aerofoil. As we discussed with the Bernoulli's principle, the airfoil is designed with a curved surface and a flatter lower surface. This specific shape forces the air to travel faster over the top of the wing, which in turn creates low pressure under the wing compared to the higher pressure area below it. This pressure differential results in the net upward force that we call it as lift. Generating lift is one thing, by controlling aircraft is another. This is where the control surface comes into play. These are small hinged sections on wings and tail that manipulate the airflow to change the drone's altitude and direction. To control the drone's roll or its side-to-side tilting, it uses ailerons located on the wings. To control the pitch, which is the nose up or down movement, it uses elevators on the horizontal part of the tail. And to control the yaw, the side-to-side movement of the nose, it uses rudders on the vertical part of the tail. Of course, For the wing to generate lift, the drone must move forward. This is where the thrust and drags comes in. The thrust is the force that pushes the drones forward through the air and typically generated by propellers or small jet engines. Opposing this forward motion is drag, which is aerodynamic resistance the drone encounter as it moves through the air. To maintain a steady forward flight, the force of thrust must be greater enough to overcome the force of drag. This reliance on aircraft aerodynamic lift is precise, what makes the fixed wing drone so efficient, that are generally much more energy efficient than multi-rotor, especially for longer duration and long distance flight. However, this efficiency comes with a trade-off. Their flight envelope or the range of their performance capacity is typically characterized by higher speed and significantly less maneuverability when compared to multirotors. Because of this, the optimization of the wing design and overall shape of the airframe is absolutely crucial for maximizing the drone's endurance and range. On our next slide, we will look at the specific control system that manages these surfaces. We just identified the primary control surfaces on fixed wing drone, the ailerons, elevator, and rudder. Now, let's look at the control system that brings them to life. What does a command from the pilot or the autopilot translate into a physical movement of these surfaces to steer the aircraft? Let's quickly review how each control surfaces work. Ailerons are responsible for controlling the drone's roll. They work by creating a differential in lift on the wings, which causes the aircraft to back or tilt to one side. Elevator, which is located on the horizontal tail stabilizer, controls the drone's pitch or its nose up and down motion. It does this by changing the angle of attack of the horizontal stabilizer. Finally, the rudder found on the vertical tail stabilizer controls yaw. It, it detects it deflects the airflow, which pushes the nose of the drone to left or right side. These surfaces are physically moved by small motors called servos, which operates based on the command sent from the flight controllers. This all comes together in the flight control system, which functions as a continuous feedback loop. The flight controller is the brain of this operation. It constantly receives inputs from two sources: the pilot's command sent via the radio transmitter and the data from the drone own onboard sensors like the IMU and the GPS. The flight controller process all this data and then send the output signal to the servos. These servos then move control surface to manipulate the drone's flight path as required. Modern flight controllers for fixed-wing drone can do much more than simply rely on pilot's command. They are capable of providing stability augmentation, which means that they automatically make small adjustments to keep the flight smooth. They also enables powerful autopilot function, including complex waypoint navigation, where the drone can autonomously follow a pre-programmed flight path. This method of using control surfaces is fundamentally different from how multi-rotor drone is controlled. In our next slide, we will compare this to the control system used for multi-rotor drones. We just saw how a fixed-wing drone uses physical control surface to steer. A multi-rotor drone, however, operates on a completely different control philosophy. It has no ailerons, rudders, or elevators. Instead, it achieves all its movement and stability by precise and independent controlling the rotational speed of each of its motors. Just in a fixed-wing drone, the flight controller is the central processing unit, act as the brain of the entire operation. Its primary objective is to receive and produce a constant stream of data from its various onboard sensors. The most important of these is the IMU, or the Inertial Measurement Unit, which provides the flight control with data on drone's orientation, including its pitch, roll, and yaw, as well as its acceleration. Another key sensor in is the barometer, which measures atmospheric pressure to help the drone maintain a constant altitude. And of course, the GPS provides the drone's geographical or a geographical position, which is essential for navigating and autonomous flight mode. After processing all this incoming sensor data, the flight controller sends the command out to the electronic speed controller, or the ESCs. Each ESC's job is to regulate the speed of their assigned brushless motor, and it does so independently of each other. It is by making thousands of these small adjustments every second to individual motor speed that the drone is able to achieve complex maneuvers and maintain its stability. Every movement from hovering in place to flying forward is accomplished by varying the thrust from each propeller, while the fixed-wing drone control its flight by deflecting the air with surface. The multi-rotor control its flight by directly manipulating thrust. This method is less energy efficient but allows for a greater maneuverability. This constant process of adjustment brings us to the important concept of aerodynamic stability. which we shall explore in the next slide. I have talked a lot about how drone is controlled, but a related and equal important concept is stability. In aerodynamics, the stability refers to an aircraft's tendency to return to its original flight path after being disturbed by an outside force, such as gust of wind. It is a crucial characteristic for both safety and ease of control. There are two main types of stability we need to consider: the static one and the dynamic. First, let's look at the static stability. This is defined by the initial tendency of the aircraft to return to its original equilibrium state immediately after being disturbed. There are three possibilities. An aircraft with a positive static stability will immediately start to return to its original state after being disturbed. This is desirable characteristic for a predictable aircraft. An aircraft with neural static stability will simply remain in its new disturbed state and will not try to correct itself. Finally, an aircraft with negative static stability, which will continue to move further away from its original state after a disturbance. This is slightly unstable and difficult to fly. Static stability describes the aircraft's inertial reaction, but what happens over time is described by dynamic stability. This is defined as the tendency of an aircraft to damp out oscillation over time after a disturbance. Again, there are three steps with positive dynamic stability, and any oscillation will decrease over time until the aircraft settles back to steady flight. This is the ideal safe condition with neutral dynamic stability. The oscillations will remain constant and never stop, and with negative dynamic stability, the oscillation will actually increase over time, getting worse and worse until this aircraft become uncontrollable. This is crucial for drone because a multi-rotor drone is inherently unstable. It has a negative static stability. It is only through the constant high-speed correction made by the electronic flight controller and the sensor, like the DJI EA2 system picture here, that it can fly. Electronics are what provides the stability. This electronic stability is the foundation for the different flight modes that pilots uses, which we'll explore in the forthcoming slide. We just established that for multi-rotor drone, stability is provided electronically by the flight controller. This ability to assist the pilot is the foundation of various flight control modes that are available on most drones. These modes essentially determine how much the drone does for you, ranging from no help at all to a great deal of assistance. Let's look at the two most fundamental modes. First, we have manual mode. In true manual mode, the pilot has direct and unfiltered control over drone's movement. The flight controllers provide no electronic stabilization or assist whatsoever. The pilot's stick input are translated into motor's commands. If the pilot lets go of the control, the drone will not self-correct itself. It will continue along whatever the altitude or the trajectory it was commanded to follow. Because of this, flying in manual mode requires a significant amount of skill and practice to master. It is preferred mode of FPV drone racing and acrobatic freestyle flying because it grants the pilot complete authority over the aircraft, but it is extremely difficult for beginners. For this reason, most people begin their journey with stabilized mode. This is the first and most crucial level of electronic assistance. In this mode, the flight controller actively helps the pilot to work to maintain level flight. If the pilot lets go to the stick control, the drone will use its sensor to automatically return to the level orientation. The system also automatically corrects for external disturbance such as gust of wind. The pilot still has full control over drone's direction, but the drone itself handles the thousands of micro adjustments needed every second to stay stable. This assistant makes the drone significantly easier for beginners to fly. So we have a clear distinction. The manual mode provides total control without a safety net, while the stabilized mode provides an auto-leveling safety net that brings that makes the flight more accessible. But the assistant doesn't stop there. Modern drone often offers even more advanced flight mode, which we will explore in the next slide. We just covered the stabilized mode where the drone assists the pilot by keeping itself level. Modern flight control can take this assist even further by using additional sensors, automate more of the flying process. Let's look at two of the most common advanced flight modes, altitude hold and GPS hold. First is the altitude hold mode. In this mode, the drone will automatically maintain a constant altitude. It is achieved by using a barometer to measure atmospheric pressure or, in some classes, an ultrasonic sensor to gauge its height above the ground. With altitude hold engaged, the drone manages its vertical position, freezing the pilot control all horizontal movement. This significantly simplifies the flying because it removes the need for constant throttle movements to keep the drone from drifting up or down. This allows the pilot to concentrate more on the task like framing a photography or navigating around obstacles. The next level of a system is the GPS hold, which is also known as position hold mode. In this mode, the drone uses its onboard GPS data to maintain both constant altitude and fixed horizontal position. If you engage this mode and let go of the control stick, the drone will stop and hover in the precise spot, actively using its motor to fight against the wind and maintain its coordinates. This capacity is ideal for application like aerial photography and videography, as it provides a perfectly stable tripod in the sky from which to capture image and video. It is crucial to remember that for this mode to function correctly, the drone must have a strong and reliable GPS signal. These advanced modes represent another layer of autonomy, making complex tasks much easier and safer to perform. The next logical step is to have drone not just holding a single position, but to navigate between multiple positions on its own. We will look at these fully autonomous navigation mode in the next slide. We have seen how drone can assist a pilot by holding their altitude and position. Now, we'll take a final step into the realm of true autonomous navigation, where the drone can execute an entire mission on its own from takeoff to landing without any real-time input from the pilot. This is where the drone's full potential as an intelligent robot is truly unlocked. The most common form of autonomous flight path is the waypoint navigation. In this mode, the drone can follow pre-programmed flight paths that are defined by a series of GPS waypoints. The pilot typically uses ground control software to pilot a course of on the map, setting a specific point that the drone need to fly in sequence. Once this mission is uploaded to the drone, the flight controller takes over and autonomously guides the aircraft from one point to the next. This powerful capacity is the backbone of many professional drone operation and is used extensively for automated surveying, large-scale mapping, and surveillance mission. However, flying autonomously would be an incredible risk if the drone couldn't perceive and react to its environment. This is why obstacle avoidance is such a critical component of modern autonomous system. To achieve this, drone utilizes a variety of sensors, such as the ultrasonic sensor, LiDAR, or vision-based camera to detect obstacle in their path. When an obstacle is detected, the flight control processes this sensor data in real time, and it makes a decision to alter the drone's course, automatically rerouting it to avoid a collision. This ability to see and react is absolutely crucial for safe autonomous operation, especially when flying in a complex environment like a forest or an urban area. True autonomous navigation is a combination of these two technologies. Waypoint navigation gives the drone ability to follow a plan, while obstacle avoidance gives the intelligence to adapt when the plan encounters the unpredictable real world. Together, they enable together they enable drone to perform complex tasks safely and repeatedly with minimum human oversight. The foundation of all these autonomous behavior is the controller's ability to maintain perfect stability, which we will look at the next slide. We have explored the incredible autonomous capacity of modern drone. Now, let's take a focused look at the absolute heart of this technology, multi-rotor stabilization. This is the process that allows an inherently unstable machine to hover perfectly still and fly with incredible precision. This is a capacity born from partnership between flight control and inertial measurement unit or the IMU. As we establish, the flight control is the brain of the multirotor. Its primary job is to maintain stability and enables precision maneuverability. It accomplishes this by constantly receiving data from the drone's onboard sensor and then sending control signal to the ECS to ensure aircraft maintain level flight. Most critical sensor for this task is the inertial measurement unit or the IMU. The IMU is a key sensor for flight control and stabilization, providing the raw data the flight controller needs to understand this own motion and orientation in space. The IMU is not a single sensor, but a suite of sensors working together. It includes rate gyros, which measure the drone's angular velocity and orientation, telling the flight control how fast it rotates, on any axis. It also contains accelerometers, which measures linear acceleration and help determine drone's orientation relative to the force of gravity. This is how the drone knows which way is down. To determine its heading, the IMU uses a digital compass or magnetometer. Finally, many systems incorporate pressure sensor like parameter, which is used for altitude estimation. This creates a high-speed feedback loop. IMU constantly tells the flight controller, I am rotating this fast, I am tilting at this angle, and I am facing this direction. The flight control processes this data thousands of times per second, comparing it to the desired state, and constantly calculates the capture. It then sends command to, to the ESC to adjust motor speed, counteracting any deviation. This partnership between the IMU sensing and the flight controller processing is the very essence of multi-rotor stabilization. To customize these capacities, developer will use specialized software tools, which we'll look at the next slide. We have seen the incredible complexity and the power of drone's flight control and its software. But what if the user wants to extend the functionality or create a complex application for specific industrial tasks? This is where the software development kits or SDK comes in, and the application programming interface or API comes into play. These are the essential tools that open up a drone platform to a wider world of software development. Let's start with SDKs. The software development kit provides a collection of tools, code libraries, and documentation that developers can use to create custom applications for specific drone platform. The primary purpose of SDK is to simplify the interaction with drones' complex hardware and software features. For example, instead of developer needing to write a low-level code to control the camera's gimbal, the SDK provides a pre-built function to do so easier. This dramatically speeds up the development process. The most major manufacturers offer these tools, which common examples include DJI SDK, the Parrot SDK, and the PX4 Autopilot SDK. Closely related to SDKs are APIs, are also known as or abbreviated as the Application Programming Interface. An API is a set of rules and definitions that dictates how different software components should interact with each other. It serves as a bridge, enabling clear communication between the drone's internal systems and external third-party application. API allows developer to access the drone's data, flight control its flight, and integrate its capacity with other services. For example, an API could allow a custom mapping application to automatically send a flight plan to a drone and then receive the resulting survey data. Because of this, APIs are absolutely crucial for building the complex integrated drone solutions and autonomous systems that are becoming more common today. In essence, SDK and API are the vital link that connects the world of software development with the world of drone hardware. They empower developers to innovate and create custom solutions that harness the power of this aerial platform for constantly growing list of specialized tasks. This concludes our detailed look with design, fabrication, and programming of drone. Let's have a quick summary in the next slide. Over the course of this unit, we have embarked on a comprehensive journey into the world of drone technology, dissecting these complex missions from every angle. The goal is to synthesize everything we have learned, weaving together the distinct but interconnected topics of classification, hardware, fabrication, autonomy, and flight mechanics. We'll revisit the essential concept from the broader categorization of unmanned aerial vehicle to specifics of their remote control operation, creating an holistic picture of how a drone is conceived, built, and flown. We'll start by reviewing how classifying drone and essential parts that make them up. Drone or UAVs are broadly classified based on several key characteristics, including their weight, size, and physical configuration. These configurations primarily include fixed wing drone, which relies on aerodynamic lift like an airplane, multi-rotor drone, which uses propellers for direct lift, and advanced hybrid design that combines these features, such as vertical takeoff and landing or VTOL. Regardless of their classification, nearly each drone is built from a core set of components working in synergy. The main body or the frame provides the structural skeleton. The propulsion system consists of propellers that generates thrust, brushless motor that spins them, and electronic speed controller are the ESCs that regulates the motor speed. The entire system is powered by an energy source, typically an LiPo battery. The brain of the operation is the flight control, which processes information from a suite of sensors. including the crucial inertial measurement unit or IMU and the GPS module. The technical functions of each component is precisely defined. The propellers are engineered with specific size and pitch to efficiently grip the air and create lift. The brushless motor are used for their high efficiency and power to work ratio, providing torque needed for flight. ESC acts as the intermediary, converting the battery's DC power to AC for motor and translating the flight controller's command into a precise changes in motor speed. The flight controller itself is a sophisticated processing unit running complex algorithms to maintain stability and execute commands. This stability is paramount in multi-rotor, which are inherently unstable and relies on high-speed feedback loop between the IMU, which senses motion, and the flight controller, which corrects it. The constant stabilization is the foundation for all other flight capacities. The journey from the concept to a flying machine is structured engineering process of design and fabrication. It begins with a requirement analysis to define the transmission, followed by the conceptual and detailed design phase, where the components are selected and the airframe is modeled. The fabrication involves a variety of techniques from 3D printing for rapid prototyping using materials like ABS and carbon fiber filaments to composite layup for high strength part and CNC machining for metal components. The final stage is assembling and integrating. When the frames is built, the electronics are meticulously wired and the software is configured and calibrated before rigorous flight testing. The level of autonomy a drone process is directly linked to the sophistication of its energy source and its programming. As we noted, most drone uses lipo batteries, but their limited energy density makes flight time a constant challenge and a key area of research. This energy powers the drone's ability to operate autonomously, a capacity that is transforming industries. In precision agriculture, IoT-enabled drone autonomously follows flight path to spray pesticides, while in logistics, they are being developed to carry payload and make deliveries. This intelligence is made possible through drone programming, while the core firmware is often written in high-performance language like C++. The developer can create custom application using various languages and tools. Software development kits or SDK and application programming interface or API provide building blocks for developers to interact with drones system, enabling a vast ecosystem of custom solutions. This programmability allows for a spectrum of flight mode that defines the level of pilot assistance. In full manual mode, the pilot has the direct control with no electronic assistance requiring immense skill. In stabilization mode, the flight controllers enables by automatically keeping the drone level much easier for a beginner to fly. The most advanced mode leverages sensor to automatically specify tasks. Altitude hold mode uses barometric to maintain constant flight, freeing the pilots using a constant throttle adjustment. The GPS hold or the position hold uses GPS data to lock the drone in a specific location in the sky, makes it ideal for photography and videography. The pinnacle of this waypoint navigation, where the drone autonomously fly a pre-programmed route, often integrates with obstacle avoidance system for safety. This entire system is tied together via a remote control link, often uses Wi-Fi or other radio frequency, which not only sends the pilot command to the drone, but also receive telemetric data like live feedback and other battery and other information. In conclusion, the modern drone is a marvel of integration. It is a synergist system where lightweight materials, aerodynamic configuration provides the potential for flight. That potential is realized by propulsion system of batteries, motors, and propellers, all governed by physical laws of propulsion mechanism. This flight is made stable and precise by tireless electronic brain, the flight controller, which process the flood of sensor data, and finally, the drone utilizes it to unlock the layers of software and range of flight mode that allows for everything from a direct manual control to a fully autonomous thing. From this basic classification to its most complex autonomous mission, the drone represents the convergence of nearly every field of modern engineering. Thank you.